We physicists have waited 100 years since 1916 for this photograph.
For decades, black holes have remained some of the most enigmatic objects in the cosmos, drawing the curiosity of scientists and the public alike. Recently, theoretical physicist Michio Kaku has shocked the scientific community with an astonishing revelation. We may have finally discovered what lies inside a black hole. This announcement is not just another advancement in astrophysics. It redefines our understanding of space, time, and the fundamental nature of reality itself. Before we start, smash the like and subscribe buttons for more updates. The breakthrough centers on a new model of black hole interiors, based on the synthesis of quantum mechanics and general relativity. Traditionally, black holes have been described by Einstein's theory of general relativity, which paints them as regions of space-time exhibiting gravitational acceleration so strong that nothing, not even light, can escape their pull. According to this model, any matter falling into a black hole is irrevocably drawn to its central singularity, a point of infinite density where the known laws of physics cease to operate. For years, this singularity has been an unsolved puzzle, a shadowy region beyond the reach of empirical verification. However, Kaku's announcement signals that this mystery may be starting to unravel. At the core of this development is a revolutionary hypothesis rooted in string theory and quantum information. Kaku and his team have been working with quantum gravity models that attempt to unify the large-scale structure of general relativity with the probabilistic nature of quantum mechanics. Using advanced simulations and new data gathered from gravitational wave detectors and the Event Horizon Telescope, the team has proposed a theoretical structure inside black holes that is far more complex than a mere singularity. Rather than a point of infinite density, the center of a black hole may harbor a fuzzball, a concept proposed within string theory. This idea replaces the singularity with a dense, tangled web of strings, which are the fundamental building blocks of the universe according to string theory. These strings vibrate at different frequencies, giving rise to all the particles and forces we observe. If Kaku's team is correct, the interior of a black hole is a compressed sphere of quantum information, held together by gravity but not collapsing into a singularity. This would mean that instead of being a dead end in physics, a black hole might be a bridge to understanding the quantum nature of the cosmos. The implications of this are staggering. For one, it addresses the long-standing black hole information paradox, a problem that arises from the contradiction between quantum mechanics and general relativity. According to quantum theory, information about a physical system can never be lost. But when matter falls into a black hole, classical theories suggest that the information it carries is destroyed forever. This contradiction has puzzled physicists for decades. The new theory, however, proposes that information is not lost, but instead encoded on the event horizon or within the fuzzball itself. This maintains consistency with quantum mechanics and brings us closer to a unified theory of everything. One of the most fascinating consequences of this theory is the potential redefinition of what a black hole actually is. No longer is it merely a vacuum cleaner of the cosmos, a monster devouring everything in its path. It becomes a sophisticated information processor, possibly even a storage device containing the history of everything it has consumed. If we could access this information, we could theoretically reconstruct the past of entire star systems or even civilizations that were consumed by these titanic structures. While we are far from being able to do this in practice, the very idea reshapes how we view black holes, not as destroyers, but as archivists of cosmic history. This interpretation also opens up new avenues for exploring the multiverse theory. If black holes contain compressed dimensions or regions governed by quantum laws, then each black hole could be a gateway to another universe or a different sector of the multiverse. Kaku's findings have reignited discussions about wormholes and Einstein-Rosen bridges, once thought to be the realm of science fiction. With the interior no longer being an unknowable singularity, it becomes possible, at least in theory, to consider the traversal of black holes not as a suicidal plunge into oblivion, but as a voyage through a quantum tunnel to another reality. The technology used to reach these conclusions also represents a quantum leap forward. Advances in gravitational wave astronomy have allowed scientists to hear the ripples caused by cosmic collisions involving black holes. These signals carry information about the mass, spin, and even potential internal structure of black holes. Meanwhile, the Event Horizon Telescope has delivered the first ever images of a black hole's event horizon, providing a visual outline of these invisible giants. Kaku's team combined these data streams using sophisticated algorithms and quantum models to simulate what must be happening beyond the event horizon. These simulations revealed unusual patterns that cannot be explained by traditional singularity models. For example, certain gravitational echoes, faint reverberations in the wake of black hole mergers, suggest that space and time behave in exotic ways near and inside the event horizon. These echoes point towards structures that align with string theory's predictions. Though indirect, these pieces of evidence create a compelling case for the fuzzball model and the idea that black holes are not empty voids, but vibrant quantum objects. Such revelations have philosophical implications as well. The realization that black holes may encode information and preserve the essence of what they consume brings new meaning to the concept of continuity in the universe. It challenges the notion of finality and loss, suggesting instead that nothing truly disappears from the cosmic stage. Even in death, stars may live on, not just in the remnants they leave behind, but in the quantum imprints recorded within the black holes they feed. This notion is deeply transformative. It recasts black holes from cosmic executioners into custodians of the universe's memory. The thought that the atoms of ancient stars, the energy of long-extinct planets, and perhaps even the consciousness of intelligent beings might persist in some form within the interior of a black hole is not just poetic, it's grounded in cutting-edge physics. Kaku's revelation compels us to reconsider our relationship with the universe. We are not merely passive observers looking out into space. We are participants in an information-rich cosmos, intricately connected through a web of quantum entanglement. The nature of time itself may also need to be revised in light of these findings. Inside a black hole, time behaves radically differently than in our familiar world. According to some models, time could become spatial in character, suggesting a realm where past, present, and future coexist in a static state. If this is true, then what exists inside a black hole is not just the matter it has consumed, but every moment associated with that matter. This opens up the tantalizing possibility that time travel, long the domain of speculative fiction, may find a theoretical foundation within black hole physics. Michio Kaku's announcement also reinvigorates the quest for a theory of everything, a single, unified framework that explains all physical phenomena. The compatibility between the fuzzball concept and string theory could serve as the bridge between quantum mechanics and general relativity that physicists have sought for over a century. This development makes the seemingly impossible task of reconciling the macrocosmic and microcosmic realms appear not just plausible but inevitable. The black hole, once thought to be an obstacle in this quest, may actually be the key. Another intriguing consequence of the new model involves Hawking radiation, the process by which black holes gradually evaporate over immense periods. Previously, this radiation was thought to carry little to no information, simply representing the slow death of a black hole. But if the interior structure encodes data, then Hawking radiation could be subtly influenced by the information inside. This would mean that black holes do not merely fade into nothingness, they may emit a whisper of their secrets before they vanish. Extracting and decoding this whisper could offer humanity a new way to study objects that lie far beyond our reach. Moreover, this breakthrough challenges existing boundaries between what is knowable and what is not. For much of scientific history, the event horizon has represented a boundary of ignorance, a point beyond which no information could return. But Kaku's model undermines that limitation. By viewing the event horizon not as a wall, but as a veil that can be decoded, the black hole becomes less an abyss and more a vault, its secrets protected, but not inaccessible. This conceptual shift may inspire new technologies aimed at deciphering the patterns embedded in radiation or gravitational waves emitted by these exotic entities. The resonance of this discovery extends beyond science and into culture. Artists, philosophers, and writers will inevitably grapple with the symbolic implications of a cosmos where nothing is lost, where even the deepest voids are filled with information and structure. It transforms black holes from icons of nihilism into symbols of resilience and transformation. The idea that knowledge, matter, and possibly even consciousness persist inside these celestial engines taps into humanity's deepest yearning: to be remembered, to be preserved, to be understood. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on black hole secrets Michio Kaku just revealed? We want to hear from you. Thank you for watching and see you next time.